Hello, good day, good morning to you all. I hope you're feeling good. I hope you are all healthy and that you will enjoy today's webinar on the topic of current transformer testing with ICT1. My name is Andrei Shepcic and I function as a regional area manager inside of Altanova Group. And I have the privilege to show you today how we test current transformers using our latest test set. First, we're going to answer what a current transformer is. So, what is a current transformer? A current transformer is a primary equipment that is used to transform current from high primary value onto a smaller secondary value. That value can be then used to be sent to secondary equipment like protective relays or energy meter devices as an information without damaging them. And the current transformer is an instrument transformer. With that, we wanted to say that current transformer is basically the eyes of protective relays and metering devices. We cannot directly connect a high primary current, which is running through an overhead line or a cable, onto a protective device like a relay or onto a measurement device, because in doing so, we would burn those devices. So in order not to do that, we need to reduce that current. Here on the right side, you can see the symbol, one of the symbols for for a CT or a current transformer, and some examples for distribution CTs or transmission CTs. Another way how we can define a current transformer is that the principal function of a current transformer is to produce a manageable level of current. Manageable, by that we mean measurable with a normal size device. That manageable level of current needs to be proportional to the current flowing through its primary winding for the operation of measuring or protective devices. So we just access this from another point of view, and we wanted to say again that this is something which will allow us to measure a high current. I also want to return to the concept of primary and secondary test sets. Since we produce test sets very often, we are asked, do you have a primary test set or a secondary test set? So for those of you who are not clear what is a primary and what is a secondary, we can say that the primary test set is a test set that generates higher currents and voltages. We can say on the left side, so on the primary side, while the secondary test set is a test set which generates lower currents and voltages. So these higher or lower currents and voltages can be simulated with some other types of devices, like devices which are directly connected to the relays, while the primary currents and voltages are something which is actually on the cable or on the overhead line or something like that. So this is something which we also deal with. So in order to be better acquainted with the nomenclature, we use also primary and secondary test sets. ICT1 is a secondary test set, even though it can generate high voltage. So let us talk about a current transformer. Let us talk about transformers in general. One of our Einsteins, local Einstein, let's say our R&D manager that used to be with us, now it's in pension, but still very active, Primo Lodi, said, a transformer does not know what it is. So what did he want to tell us with this? He wanted us to be aware that the transformer has always a primary and a secondary winding. And actually, depending on how we connect the source and the user, we can change the functionality of the transformer. So if we have, as in this example, 10-to-1 transformer, that means that 10 volts on the primary side will give us 1 volt on the secondary side. We can see here in the transformer, we always have the voltage on the primary side, the current on the primary side, and then we have the ratio of windings. The ratio of windings is what defines whether this is a step up or a step down transformer. So we will see in the next slide that since the power needs to be always the same on the primary and on the secondary side, of course, we need to take into consideration that there are some losses, but for the sake of explanation, we will for now neglect them. We can then write it as a multiplication of input voltage and input current equals output voltage and output current. So if we have a 10-to-1 transformer, like we mentioned before, That means that if we have 10 volts in the primary, as you can see in example 1, we will have 1 volt on the secondary. But the trick is, since the multiplication of the current and voltage needs to be always a fixed number, if we will decrease the voltage 10 times, we will increase the current. So in this case, we have the actual opposite of a current transformer. 10 to 1 ratio tells us that voltage will be decreased, but the current will be increased. With the CT, we decrease the current. And that decreased current can be seen in example number 2. So a current transformer will always have more turns on the secondary side than on the primary side. On the primary side, it will usually have maybe 1 turn or 1 or maybe 2 turns, rarely more than that, because we want to have a bigger voltage on the secondary side, which means more turns, which means less current. So to make it simple, in the example number 2, if we have 10 volts and 10 amps on the primary side and the ratio of 1 to 10, on the output we will have 10 times bigger voltage, but at the same time 10 times smaller current. And I'm sure that most of you understand this. You could also say that a CT is a step-up transformer that effectively increases the voltage and reduces the current proportionally. This word proportionally, it's very important because you will see that there are a lot of tests which test this proportionality. Apart from ratio, there are some indirect tests which test the proportionality. The point being is that we always want to have, for a certain type of CTs, on the secondary side, what we have on the primary side correctly transformed, but in some other cases, we don't want to transform after a certain value because we want to protect certain devices. So after explaining all this, let us become a little bit more technical. Excuse me just for a second, I need to start the presentation here again because my pointer was not showing. So I hope you can see my pointer now. And here what we can see is what is the scheme, equivalent scheme of a current transformer. Actually, this is the equivalent scheme of any transformer. So we have, of course, the primary side and we have the secondary side. And on the primary side, we have the primary current running into the primary winding. And then since we have a core, that core is helping us move all this electromagnetic force to the secondary side. On the secondary side, we have, of course, we have IX and IRM, and we can see that these are the losses. So these are the losses in the core. These are the losses in the core because the core gets magnetized, and also the core has some eddy currents running inside. So due to that, we do have some losses. And after that, what we see is the EMF, the electromagnetic force, E0, which is then the force which pushes the electrons. This is basically the voltage, which creates the current IS. That current has to pass through the resistance, RCT, of the windings of the secondary side, and then also when we connect our measurement device, by that I mean protective relay or a metering device, that is here represented by RB and XB. So if we look at the vectorial presentation, we see on the y-axis US. US means the voltage on the secondary side, and to that voltage we need to add the voltage drop of IS times RCT, which is the voltage decline on the resistance of the secondary side winding. The sum gives us the EMF electromagnetic force. And then also, as we can see here, we have the IS added to the I epsilon, which are the losses in the core, which in total gives us the vectorial sum of IP, which is the primary current, which produces all this flux, which is then translated and produces the electromagnetic force. We have some losses, as we said here, IX and IXM and IRM, and we see that they're 90 degrees shifted because this is in phase and this is the 90 degrees delayed, and the sum of that gives us the I epsilon. So this is the inner workings of a CT. And now in the next picture, we will see the inner workings of a CT when we actually, let's say, take it apart. If we want to take apart a CT, we will see that that particular CT has a primary terminal which extends onto a primary winding. So we have a winding here. The current which is passing through this winding creates an electromagnetic field, and then this electromagnetic field using the core is moved onto the secondary winding. We see this is the secondary winding, this is the secondary side. Then we also need to have some insulation, the internal insulation, graded insulation, and outside porcelain insulator, and then we have here a terminal box for the connection of the secondary side. So this secondary side is extended onto this box, and here we will have usually a few taps in order to be able to connect few measurement devices. One other design which shows us some other aspects is this design here. We need to keep in mind that when we connect the primary side here on the 0.5, if this gets heated up, also we need to cool it down. So that's why we often have some mineral oil in a tank like this. And here, if this mineral oil gets heated up, this needs to expand a little bit. So this is an expansion device which allows the expansion of the oil. And also, as it is expanding, you can see here what is the oil level. Other elements are the same as in the previous CT. We have the insulation inside, and we have, so that's in this case paper oil insulation, and on the outside we have a porcelain insulator. And again, we have here the connector, the connecting part, so the secondary terminal box, and a solid base needs to be planted. Why? Because these devices, especially if we talk about transmission, are planted on a pole, and here you can see how one is installed in a substation. This is that similar CT while it's still, let's say, in the factory, and we can see the top covers which we saw before, which are holding the part with the oil. We can see the place where we connect the primary side. We can also see the porcelain insulator from the outside and the secondary termination box. So this is how do these transformers look like when they are in the substation. So as you pass through the substation, they're always, we need to know that they're always connected in series, because current transformers, if you want to measure current, need to be connected in series, and that's how we see that connection right here. Now, and of course, let's say the base, which we mentioned before. If we talk about the types of CTs, the types of CTs from the point of construction, from the point of view of construction, can be a bar primary type, and these are much more common for currents bigger than 100 amps. And we also have a wound primary type. In this case, these are a little bit less common. They are made for smaller currents. Now, these two types, this is from the point of view of construction, but more important differentiation when it comes to transformers comes from the functionality of that transformer. I'm sure all of you have heard about the metering CT and the protective CT, and they're both CTs. It's like the car and the bicycle are transportation vehicles, and the same way like a helicopter and an airplane fly in the air, but they're not the same. They both fly in the air, they're both transportation vehicles, but they're used for different purposes. Of course, sometimes you can intercross and use them for similar things, but in general, there are differences. So let's first see what are the biggest differences between a metering CT and a protective CT. Well, we'll put it bluntly, it's the knee voltage and the accuracy. The knee voltage for the metering CT is at a very low voltages, few volts or few tens of volts. We will see that in the upcoming slide. And for the protective CT, the knee voltage is very high. The knee voltage being high means that the current will be accurately transformed from the primary to the secondary side, even for high currents, much higher than nominal value. For metering CT, that is not necessary. Actually, that is forbidden because we want to protect the sensitive inputs of the metering equipments when the current is too big. So this is the knee voltage. The second thing is accuracy. The accuracy of metering CTs is often very high, and the accuracy of protective CTs is often much lower because they need to be robust. They don't have to be very, very accurate. All this I put in this next slide. I will just tell you a short story. I mentioned it last time. I find it very interesting and useful. In one of the sequels of Mad Max, you had the Master and the Blaster. Master Blaster was basically one entity made of two beings. One of them was a small person, and he was the brains of the tandem, and the other person was a very big person. He was a strongman, but let's say that his mental capabilities were not that developed. They function perfectly together because they basically they had to function like this. But how do we compare this to the metering CTs and protection CTs? The metering CT is the master in a sense that it's very accurate, and it definitely, he's the one, let me put it like this, that counts the money, because this is the CT which is connected to the energy meter, which calculates how much energy have you sold or bought from somebody. So it has to be very accurate. And the protective CT is there to protect the system, and it needs to tell the protective relay exactly what is happening, exactly what is the current when you have the fault. So let me put it like this. Metering CT needs to function perfectly when there are no faults. For that period, protective CT is not important. When the fault happens, that's when the protective CT needs to jump in. So in short, metering CTs need to be very accurate, up to 100 or 120, sometimes even 200%, but mostly 120% of nominal or full load current. Above that value, it needs to saturate to protect the inputs of the instruments under fault conditions, as we mentioned, and it often has a very sharp magnetization characteristic. The knee point voltage, usually only few volts or few tens of volts. We will explain that in the upcoming pictures, while for the protection CTs, it needs to accurately transform a wide range of currents. As we said, they need to function perfectly when there is a fault. And when there is a fault, the currents are 10, 20, or 30 times bigger than the nominal current. If the nominal current is 100 amp, then when you have a fault, it can easily be 2000 or 3000 amps. The saturation should be avoided at all costs. Why? Because if when we have a fault, we have a wrong information, how much is the current on the line, our protective relay, for example, if it's a distance relay, will not be able to know exactly how much is the current running through the line, and will not be able to calculate where the fault is happening, what is the zone in which the fault is happening. And because of that, it might trip in a wrong zone, it might open too soon or too late. Or even better, if we have an overcurrent relay, the overcurrent relay can have two or three setups, two or three stages. For example, from 1 time nominal to 5 times nominals, it should trip in 800 milliseconds, and from 5 times nominal on, it trips instantaneously. If the protective CT doesn't read correctly what is the current, it might trip in 800 milliseconds and should have tripped right away. So taking that into account, this is something which needs to give us a very accurate information. And in order to give us a very accurate information, the knee point usually should be very high. The knee point should be very high, and this is what we want to turn to right now. What is actually the knee point? So the ISC 61869 defines the knee point as the voltage at which the 10% increase in applied voltage to the secondary side increases the magnetizing current by 50%. So for voltages greater than the knee point, the magnetizing current increases considerably, even for small increments in voltage across the secondary terminals, as we can see here. IEEE C5713-1 tells us that the knee point is the intersection of the excitation curve with the 45-degree tangent line in the knee point. What they all want to say is that actually this tells us at which point is the ratio between the primary and the secondary side stopping to be accurate. So if we had a protective CT where up to 30 times nominal current, it was possible to see a good ratio on the secondary side. If we have 40 times nominal current, the output will saturate. What I want to say by this is that if we go over the knee point, even if the current increases on the primary, it will not increase on the secondary, and we will not have a correct information. So that's why today we will be talking a lot about this knee point, and this is the example of the knee point with a metering magnetization curve of a metering CT and the magnetization of a protective CT. You see the linear part is basically, you see that the linear part is here, and then very quickly as we go a little bit above the nominal value, it saturates, and in saturation it protects the output, because as we said, if the device saturates very quickly, it will not increase the current on the secondary when the current on the primary increases. And if that changes, for the protective CT, as much as you increase the current in the primary, you want to have a correct information on the secondary side. So all this way, it will have a linear characteristic to give you a good ratio. So I hope I made myself clear when it comes to the knee point. If not, feel free to ask questions. My colleague Simone will surely give you a good answer. He's a very capable engineer who did a lot of commissionings in his experiences. Let me now talk about some other parameters which you will find when you will be testing current transformer. The first one is ALF, short for accuracy limit factor. So in order to maintain the accuracy of a CT during the fault, we need to, as we said, be linear and also tell to the user how high can they go with the primary current and still have the good transformation onto the secondary side. By that, I mean this. Let me take an example, because the easiest way how to explain this is with an example. The marking you will find on a transformer can be, for example, 5P10 or 10P30. These are the markings which talk about the accuracy of the transformer. 5P10 means that if I have 10 times, and in that case ALF, accuracy limit factor, is 10, if I have 10 times higher current than the nominal current, the maximum error at 10 times nominal current is 5%. So that means that if I have, let's say, 800 to 1 CT, and the current on the primary side is 10 times bigger, so 8,000, the error on the secondary side cannot be more than 5%. Another example is that if ALF is 30, then the 10P30, for example, we can say that if the current is 30 times higher than the nominal current, the error cannot be more than 10%. So this is ALF, and the ALF is usually used for protection CTs. I mean, usually it's always used for protection CTs. For metering CTs, we use another parameter, ISF, instrument safety factor. The instrument safety factor is simply the CT's saturation current divided by CT's rated or nominal current. So if I have an ISF of 2, that means that CT will saturate when primary current is 2 times the nominal current. So that means it will be accurate in transformation of current up to 200% of the nominal current. So this is for the metering CTs. And we also have an accuracy class as an important parameter. An accuracy class here is a rating. It is a number which is expressed as a percent. CTs have for example, if we have a CT accuracy 0.5, that means that at 100% of nominal current, the error cannot be more than 0.5%, the ratio error. There are different standard accuracy classes, 0, 1, 0 to 0.5. There is also 1 and 3, but these are more for protective CTs. And there is also so-called S accuracy class. So just to let you know what is the S, it guarantees, the S class guarantees maximum metering even for low loads. You can see, for example, if we have standard 0.5% accuracy class, which is, for example, mentioned here, you can see that for 100% of current, we need to have 0.5% accuracy. But for 5%, the accuracy can be 3 times lower, 1.5%. If we have an S type, then an S type, we can go even with a much smaller current, will be as it would be for 100% for loads from 20 to 120%. So for an S type, you could see basically here 0.2S would have 0.2 here and 0.2 here and here. This wouldn't be 0.35. So this would be our accuracy class.
Andrei, excuse me.
Simone, yes, please.
Yeah, there is a question in the dashboard that suggests me that we probably have to add one detail. If you can go 2 slides back. Okay, these numbers, ALF, that you can find in the nameplate, for in this example, 10 or 30, are valid under a specific condition. And this condition is that the burden connected to the secondary side has a value corresponding to the nominal one. If the connected burden is less than the nominal, then the actual ALF will be higher. Vice versa, if the burden is too high, the actual ALF is much less.
That is absolutely correct.
Then there is a test with ICT1 that can also tell you what is the actual ALF according to the specific value of the burden. But basically, that's the purpose of the accuracy test that you already explained in the last slides that you talked about.
Thank you for that clarification. This was something which I actually wanted to talk about later, but I think it's very important to mention that the burden is something which is very important, the amount of relays connected to the CT, and this is absolutely true. The ALF can be different depending on the burden which is connected. So yes, that is something which should be good to be mentioned also in this slide. Thank you for that comment. And let us just finish with this last slide, which talks about some standard nomenclature. This is also important. When we test a power transformer and when we install a power transformer, we need to be aware that there are standard nomenclature, standard names for the primary and the secondary connectors. There is P1 and there is P2. So, and there is S1 and there is S2. P stands for primary, S stands for secondary, and it is sometimes the names are K and L with caps lock and KLL with small lettering on the secondary side. The P1 is usually connected to, not usually, but the P1 should be connected to the source and P2 should be connected to the load. Now, also, if we want to have a correct polarity, we need to say that the current which enters P1, as you can see here, should exit S1. And this is how we defined the correct polarity. And also, you can see here that we have short-circuited the secondary side by putting an ammeter in this connection. We have basically made a short circuit because the ammeter has very low resistance. And what is important to say that this is a necessary practice to be done when you are testing a current transformer. Why is this so? Because as we remember, when we, let me just go a few slides back, when we decrease the current from 10 to 1, we increase the voltage. It is something which is a physical fact and we cannot escape from that. So we increase the voltage. In increasing the voltage, we can actually damage some of the secondary side terminals if we don't short circuit them. So in order to keep the terminals, to keep the CT safe, always short circuit the secondary side, and you always actually do that when you do a standard ratio test, for example, because if you connect the ammeter on the secondary side, you short circuit your secondary side. Of course, very often in the in the current transformer, you don't have just one tap. You have S3, S4, S5, etc., because sometimes you have more relays and you want to connect each onto onto one secondary side. So having that in mind, it is also a good idea if you're testing S1 and S2 to maybe short circuit the other ones. Now, having said that, let us show the ICT1, the star itself. So this is a device which, as we can see, is made for fully automatic current and voltage transformer testing with an integrated switch box. This effectively means that with this device, you have to have only one connection, and with this one connection, you can test all the necessary functions. So designed for current, voltage, and combined transformers, since we have to set up only once, it's time saving. Some of the main tests are ratio and phase error, excitation or knee point test, winding resistance, accuracy, burden. The 5-tap switch box is what saves the time, and it is able to test CT with saturation voltage up to 2 kilovolts. This device generates 2 kilovolts in 50 hertz or 60 hertz. So this is a real signal, and for some cases, if the knee point is bigger than 2 kilovolts, we use a situation where we generate a DC voltage and thus saturate the core, so in that way we can test the knee points up to 30 kilovolts. Also, there is an integrated demagnetizer. We need to demagnetize every once in a while, every few years, our current transformers, because in the BH plane, maybe on the hysteresis curve, the point is quite high, and even without us knowing so, if the fault comes, we can saturate without being aware that we will saturate. So integrated demagnetizer is a very useful tool, and CT Explorer function is a very useful function that if we don't have any nameplate, we just connect our ICT1 and it automatically does a series of tests, after which we can see the results of that particular transformer. The device is lightweight, 16 kilos, it's not very big, and this is the device as shown before. In the device we have a Wi-Fi for a connection. We also have a 7-inch touchscreen display. We have 6 terminals integrated switch box. Effectively, you can connect 5 taps, but to connect 5 taps, you need 6 connectors. We have an Ethernet through which we can connect with the device also, and a USB port through which we can download the results or upload some test plans. A rugged case with handle. We have an emergency stop button on the device. This is where we connect the power supply, and this is the on-off button. It's a very simple device, and you will see now how what are the differences between the two models. So we have the advanced and we have the standard model. The advanced model covers all the functions: turn, ratio and polarity in voltage mode, burden secondary side, excitation curve with the standard method up to 2 kilovolts with 50 hertz, and excitation curve with DC method where we can test the knee points up to 30 kilovolts. Winding or burden resistance, ALF, ISF test, leakage current, accuracy test, demagnetizer, and CT Explorer, the function which finds the nameplate of the transformer. The difference between ICT1 Advanced and ICT1 Standard is that the ICT1 Standard does not have the function for the indirect method of knee point using the DC. So this is the only difference. And we should also say that, of course, we abide to all of the important international standards. The old one, 60044-1257, and the new one, 61800-69, and also we abide to ANSI or IEEE C5713-1. So these are the tests that we can do on a current transformer, and on the voltage transformer we can do basic tests like ratio. Also for electronic VTs we can do ratio. We can do the no load current or the leakage test and the accuracy test of the VT for advanced and for standard ICT1s. There are no differences. The conclusion is that excitation curve using a DC method is the biggest difference between standard and advanced version of ICT1. And to answer the question why we have this function, well, we have this function because some CTs, not many of them, but the CTs above for the transmission, usually for 230 kilovolts or maybe 400 or even more kilovolts, sometimes have the knee point above 2 kilovolts. In that case, we will use a different method, and in that case, you would need to use ICT1 Advanced. So let us check some of the output characteristics of the device itself. The main generator can give us a high AC voltage, a low AC current, a low DC current, a low AC voltage, and a low voltage for excitation curve DC method. So let's take them step by step. High AC voltage. High AC voltage is usually used for the ratio test and also for the excitation curve or the knee point test, and we can go up to 2 kilovolts. And in that case, we can generate even up to 1 amp. Usually, we don't need to go that high. We go with a much lower current, let's say 0.2, 0.3 amps, but you can see that the maximum power is 2 kilovolt amps. And usually, as I said, we test with a lower current, so we can easily and very successfully do the test of AC testing, of ratio testing. Low DC current is an output which is used, basically they're all the same outputs, it's just internally switchable. This output is used to test the winding resistance. 6 amps is maximum, and the driving voltage of 30 volts allows us to do a test very quickly. You will see on the video how fast it's done. So the maximum power on that one is 180 watts. Low AC current is a test is an output we use to do mostly the burden test. Also 6 amp is the maximum, and 100 volts is the driving voltage behind. And the low DC voltage for excitation up to 30 kilovolts can generate up to 200 volts DC with a maximum output current of 2 amps. And the maximum power differentiates from 230 supply to 110 supply, 110 volt supply. In the first case, it's 400 VAs, and in the second one is 330 VAs. To mention some other detail, the frequency is not just 50 or 60. The frequency goes from 15 to 400 hertz with a resolution of 10 millihertz. And we have, of course, all types of protections on the outputs and the inputs of ICT1. Since we talk about the outputs, let us mention the accuracies. The accuracies are very high. We have, of course, the typical and the guaranteed errors, but you can see that for typical, that for all of the mentioned outputs, we have the error which is between 0.02 and 0.025. Guaranteed error is twice as high, but still we talk about 0.5, which is a very high accuracy for such a small device which can do so many functions, and it's more than comparable to all other devices in the market. Now, if we talk about combined measurement, for example, CT ratio measurement, the CT ratio measurement is performed applying the high voltage on the secondary side and then measuring the CT's primary side to calculate the error. This is kind of a little bit vice versa than what is, for example, used in our other device, STS, where we generate on the primary and measure on the secondary the current. Here, we generate on the secondary the voltage and measure on the primary, which gives us a higher accuracy. And you can see that the accuracy is between 0.02 and 0.05 for most of the CTs. The other ratios also have a high accuracy, somewhat less than the first one, but you will not often find these ratios. So it is a very precise instrument. The same goes for VT ratio testing, 0.03 to 0.2 for the first ratio range. And when we come to the burden test, which we mentioned before, of course, the burden is actually how many relays or energy meters can we provide with a signal coming from our CT or our VT when we use it properly. So we cannot connect 20 relays to one CT. We can maybe connect 3 or 4 relays and maybe 1 metering unit. So we measure the burden by applying a low AC current to the CT's burden and measuring the voltage drop. That way we know how much that is. Those values are between, let's say, 5, 20, maybe 30 volt amps, and we can see what are the voltage ranges from 3 to 130 volts and the current tests, so between 1 and 3 volts. The VAs are also can be quite high, and the resolution, including the accuracy, are more than satisfactory. Winding is a very important test because it tells us actually in most of the cases if we have some loose contacts, or maybe if we have some broken wires inside or short-circuited wires. So in this case, we use a pure DC current source, and it basically does the test very quickly. This is a very nice way how to perform the test. A resolution when we measure is 0.1 milliohm, and the typical accuracy is 0.05%. The guaranteed accuracy is 0.1%, plus or minus 1 milliohm. Phase angle measurement, when we do the ratio test, we also check for the angle, for the polarity. If we are okay, we measure from 0 to 360 degrees. The resolution is 0.01 degree, and the accuracy is less than 2 minutes typical and less than 4 minutes maximum, which is again a nice value. The applications for the ICT1 are in the factory or on the field. So in the factory, we can perform standard tests, we can perform a high accuracy CT test up to 0.1%. And in commissioning, because it's a lightweight device and you can do all the necessary tests for a CT on the site, you can easily transport it and use this one device with one set of connections to do the CT testing. Now, here we are moving on to the firmware of ICT1, and in this firmware we can see exactly what does the main screen look like. So the home page, you can, when you turn on the device, you will be able to test current, choose to test current transformer, voltage transformer, or do some control and measurement, basically use the device to generate some currents and voltage or to measure. We can then use the file manager to save some files or to open old files and to check some settings. Here we can see what does it look like when we are setting up the different number of taps or the different number of cores. So usually a CT has multiple taps. Sometimes they also have different cores. We can have a protection core and a metering core. And what I would like to show you right now is video number 1, how we set up the header in ICT1. So the video is here, and let us start. My colleague may do this video in which we are first setting up the header. And in the header, we are setting up the name of the substation. Now we are deciding which standard to use, what is the secondary current, is it 1 or 5, how many loops we have on the primary side. Here we're deciding whether this is a metering or is it a protection CT. We are saying what is the ALF. And in this step, we are defining the taps. So here we have one S5, one S4, one S3, and one S2. 600 to 1, 300 to 1, 150 to 1, and now we are going to change this 75 to 1 to 100 to 1. To show you how is that done. We can also see that we need to say what are some other parameters. There are some of them are copied. You can change them here. And in the last screen, what we see are the tolerances. So in order to have an automatic pass or fail, what we do, we say how much can, for example, the polarity be different than the nominal one, how can the burden, including the cos phi, be different in order to get a pass or a fail. So this is that part. After we do that, we say save, and then we are ready to start the test. And after we set up, we came back to the screen for the CT, where we can do ratio and polarity, winding resistance, excitation curve, accuracy, burden secondary side, ALF, ISF. We can demagnetize, we can explore our CT, and we can do a leakage current. So let's take it step by step. The first, ratio and polarity. When we do a ratio and polarity test, we generate on the secondary side the voltage, and we measure it on the primary side, as we said. In this particular example, we had 4 taps, and it was 100 to 1, 200 to 100 to 5, 200 to 5, 400 to 5, and 800 to 5. These are the actual ratios which we measured. Instead of 150, we have 151, for example, and this is the error which we have. So this was one not so accurate CT. Now we will see video number 2 for one other example, how we do this test. So video number 2 will show us how we do a ratio test on the ICT1. We choose the application, and here, if you click this button, you can see how you need to connect in order to execute this test. Now, this might be an obsolete information, even though it's not, because you always connect in the same way. You never change these connections, because this is the secondary side, and you connect it to the secondary side of the CT, and this is where you connect the primary side of the CT. Of course, the primary side has also some shielded connections in order because we have to have a very high accuracy on this measurement, and this is the connection which we keep for all the tests. Regardless, it's always good to be reminded how we need to connect. Now we will choose with what voltage we want to do the test. How many volts will we generate on the secondary side in order to do a test and measure the voltage on the primary side. So now we press the start button. The test is in progress, and we can see already that how much is actually being generated onto the secondary side, how much current is entering the secondary side, and how much are we measuring on the primary side. We are also checking the polarity. Right now, since the test is in progress, we still don't have the numbers, but very soon we will get the numbers for the whole 4 taps. In the end, we will not just have the numbers for the standard taps S1, 5, 2, S1, 4, S1, 3, and S1, 2, but we will have so-called intertaps, S2, S5, S2, S4, etc. But we are more interested in the basic ones. So right now we are already seeing some results for the 3rd tap, and when the 4th tap is done, we will be able to see all of the results. The whole test doesn't last more than a minute and a half maybe, and with that you check all 4 taps. So right now the last tap is being checked, and we are now getting the results for everything. So let's see, instead of 600 to 1, we have 600.94. We have an error of 0.15. The error is similar for the 2nd tab, 0.18, because it's not 300 to 1, but 300.54. Here, 0.13 is the error, and here, 0.12. The phase shift is also very small. M stands for milli, so 10 millidegrees, 8 millidegrees, 0.14, and 0.19 degrees. Polarity is okay. These are the values which we measured on the primary side. So just to explain, we said we want to generate 20. This is how much we generated for the 1st tab. But then for the 2nd tab, we generated half of that because we wanted to measure the same value on the primary side. This way we found we have the best possible accuracy, and since we are decreasing the voltage, we are getting the same current running in the secondary side because we have a different turn ratio. And this is what our result would look like at, of course, the test frequency of 50 Hertz. So this is core 1. Later, we can do core 2, for example, if this is a protection core. This was a metering core. So this is how we do the test for the ratio when we use ICT1. Now, the next one will be the test of excitation curve. So excitation curve is, we've mentioned before many times, a so-called knee point test. How is it done? So the high AC voltage is connected to the output of the CT secondary side, slowing the voltage and measuring at the same time the output voltage and current. So we are connected just to the secondary side. We are generating and increasing the voltage and the voltage, and at the same time we are measuring the magnetizing current which is entering the secondary side. So let us start the test. Here is the test. Now excitation curve, and in this case we will see again how the connections are done. We will use all 4 taps. We will test all 4 taps. Here we see what are the settings, what are the nominal values, and then we start the test. Of course, before we start the test, we will get a notification that we need to be quite careful, because here we can generate the voltages which can hurt somebody or hurt a person. So the first step is flux evaluation. Actually, what is being done, we are not plotting anything right now, but internally what's happening, we are increasing the voltage, and you will see the plotting of the curves when we start to decrease the voltage. We do that because that way we magnetize, and then while we demagnetize, we know in which situation we were. We know that it will not show us any wrong results. What you will actually see is that we will be plotting initially the curve for 1S1 and 1S5, because that one has the biggest knee point around 400 volts. And you can see it is starting right now. We can see the voltage being decreased here, and of course we can see how currents are small. And when this is done, we will automatically get all the curves for all the taps here, because effectively it is just the ratio which differs. With this test, we test the core, not the windings or something else. So right now we're finishing with this test, and we can see that the current is decreasing. It's basically going to 0, as well as the voltage. And we have right now the results for all 4 taps. So before we continue with the table, I just want to show you, this is for number 1. This is for number 2, the tap number 2, 1S1, 1S4. This is for tap number 3, and this is for tap number 4. We can see here the knee points, so 409, 204, 102, and 68. The nominal was 400, and as long as it's bigger than or equal to the nominal, we are okay. We can also see the results in a table form. What was the current generated when we were generating certain voltages, and we can see that for different taps. And with this, we finish the test. So this was our excitation curve test. And there is another excitation curve test, which is done through a DC method. Now, with the DC method, what we actually do, we actually saturate the core. And in saturating the core, we use a lot of mathematics and indirect methods to simulate and understand what would be the knee point for this particular CT. It uses a lot of proprietary and tested, very well made functions. And this is the only difference, just to remind you, between ICT Advanced and ICT Standard when you are deciding which ICT1 to own. So let us then move on. And yes, so this is basically the function which we measure, and then how we extrapolate that to the function in the VI plane. The video 3 is, sorry, this wasn't the video, this is for a CT Explorer. Now, the CT Explorer is a function which we said if we don't have the nameplate, or if the nameplate is damaged, or we want to test the whole nameplate, we can actually always connect the ICT1 to our current transformer, and we can start this test in order to get all the parameters of the test, of the CT. And we can see that we can get the ratio, we can get the burden, we can get the cos phi, the operating power, and also the winding resistance. So it's a very user-friendly function, and I recommend everybody to use it, especially if they're not sure what are the nominal values of that particular CT. Moving on, the next test would be the accuracy test. So we have the accuracy test for, the measuring CTs and for the protective CTs. We mentioned before, we have shown this table before, some standard accuracy classes 0, 1, 0, 2, 0, 5, and 1 have the certain accuracy bestowed upon different loads. So 100% should have the same accuracies, but 5% shouldn't have those accuracies. We can see that they're different. So for example, for 1% accuracy, when you generate 5%, you can have 3% difference, but that's what is accepted. Apart from ratio, we also need to evaluate the phase displacement, so we can also see what are the maximum errors in minutes and centiradians. So this is for the measuring CT according to the IEC 61A69-2. For the protection CTs, we can see that the 5P and the 10P have two different accuracies. So the ratio error at rated primary current cannot be at a rated, not n times different. So at a rated primary current is 1%, and for the 10P is 3%. So there is a 3% possible error, which can be assigned to a protective CT. And when we talk about phase displacement, it can be up to 60 minutes. For the 5P and for the 10P, it is not defined. So the accuracy test is also an important test in which we measure what are the accuracies at different loads for the ratio and also for the phase displacement. Winding resistance. Winding resistance is a test which shows us what is the resistance of the winding, not the impedance. So it is connected, it is measured by connecting the low DC current source to the winding of the CT and measuring the testing current and the voltage drop. Because we use a pure DC, it is very, very fast test, and this is a test which we want to show you in our last video today. So a winding test will start right now. We choose the option winding. Again, we can check the connections, which are the same for all the tests. We choose the current, let's say 2 amps, which will be generating. We will test all the possible taps. We choose the material, which is normally copper, and we start. First, we will see the measurement for the tap 5. We see we are generating 2 amps, measuring the resistance. We can compensate on that resistance, of course, in regards to temperature, and we are showing what is the measured voltage. So this number divided by this number gives us this number. And we can see that the resistance is basically 50% difference between this one, and this one, because this is 600 to 1, 300 to 1, 150 to 1, and because this is 100 to 1, it's not 50% difference between these two. And this is how we test the winding resistance. You've seen that it's quite fast. In less than a minute, we've basically, well, it's a minute and 12 seconds, but we also configured the measurement. In less than a minute, we managed to measure all the necessary winding resistances. There are some other tests I want to inform you. For example, ALF ISEP test, which we automatically execute after you've done your winding resistance and burden of the secondary side. So this is not a separate thing which you do. It's a compounded test. Leakage current, this test is actually performed by connecting the high AC voltage between the CT secondary cabling and the ground, or between the primary and the secondary windings. With this test, you are basically trying to see what would be the current running between the primary and the secondary side. Ideally 0, but it's often something different than 0. And the demagnetizer, it's not necessarily a test, but it's a very useful function, which purpose is when applying a DC current with alternate polarity, you are actually putting the system in the BH plane into the point 0, 0. So last thing I wanted to mention here is a test plan, a very, very useful feature where you can prepare in your office before testing which tests you want to do, what are the nominal values, and when you come to the site, you just connect and press start. The ICT1 can also be connected to the PC, and when you connect it to the PC, you can get results something like this. It's a very nice piece of software. This is for a multiple core situation, and with this, I actually want to close with the fact that, of course, you can print reports. They can be printed in the standard formats like PDF, Doc, DocX, Excel, etc., etc. And when you do that, you have successfully tested your current or voltage transformer with ICT1. So this was everything about ICT1. If you need some kind of help, you are always welcome to contact me at my email andrei.scpcic@altanova-group.com, or you can find your regional offices for your distributors on Altanova webpage. It has been a pleasure presenting this to you. I wish you a happy remainder of the day and enjoy. Thank you very much for your attention.